Okay, so in this video, I'm going to talk about growth rate or end behavior as x goes to infinity. We'll make this more precise in the next couple of weeks, but what I mean is I want to consider what's happening to a function as x gets really large. And when I say really large, what I mean is like if you could zoom out on the x-axis, what's happening all the way to the right. So if I could see the entire x-axis, what would happen all the way to the right. And when I say x is getting really large, the way that you should think about that is any finite number that you can think of, you can write down the largest finite number that you can think of, you should consider that small as x is going to infinity. So any number that you can think of, you should think of as small, and x is much, much bigger than that. And specifically in this video, what I want to talk about is how fast are functions growing and comparing them. So which functions are growing faster than others. So let's start with a basic polynomial, f of x equals x. And now as x goes to infinity, x grows like x, right? It's a function that's just itself. So the input is the same as the output. So this function is also tending to infinity since the input is tending to infinity. But if I were to compare that to, let's say, x squared, when x is getting really big, you can see already from the graph of f of x and f of x equals x squared that the parabola grows faster than the linear function. Another way to think of that is if I'm taking a very large number, it's large, but if I'm taking a very large number and multiplying it by itself, it's much larger. Okay, so I'm gonna use this notation, less than, to say that x squared is getting way, way bigger than x as x goes to infinity. And we'll make this notation more precise in the next couple of weeks. And similarly, if I consider the function x cubed, it's going to grow much faster than x squared. Because what am I doing is I'm taking this function and I'm multiplying it again by something really large. So it's much bigger. And this is true for any sort of sequence of polynomials or power functions. The larger the exponent is, the faster the function is going to grow. On the other hand, if I compare a power function like this to an exponential, even if the base of the exponential is something small, as long as it's bigger than 1, this should be 1.01 to the x. As long as the base of this exponential is bigger than 1, then even if the power of this function is, let's say, 10 to the 10, I take 10 to the 10 x to the 10 to the 10, then in the very beginning, this function will look a lot bigger than this function. But as x goes to infinity, the exponential function sort of grows much more rapidly. And so even though this exponent in the power function is really large, since what is in the exponent is going to infinity, this function is going to dominate. And we'll prove this later in the class. We'll prove that this is true. You can sort of see there's some intuition why this should be true if you look at the graph or if you think about what's happening with this exponential function. But we'll prove this later. And similarly to before, like if the base of my exponent is growing, so 1.01 to the x, is going to grow much slower than, let's say, 2 to the x, which is going to grow much slower than, let's say, 3 to the x, which will grow much slower than, let's say, 10 to the x. So polynomial functions, they depend on the exponent, but they grow much slower than any exponential function as long as the base is bigger than 1. And exponential functions, well, once you're in the exponential function range, then we're thinking about the base of the exponent. Some other functions that we might have seen are like logarithmic functions. So a logarithmic function is going to be much smaller than any polynomial, even if the exponent of this polynomial is, let's say, 0.01. It's not a polynomial, then it's a power function. But a logarithmic function is going to be much smaller than any power function, as long as the exponent is positive. You can see this because log is sort of flattening out a lot as x is going to infinity, and the way that it flattens out is at the same rate that the exponential function is increasing because they're inverses of each other. And again, we'll prove this later in the class. So maybe it's not completely obvious right now, but we'll prove it later. And I want to, so this is sort of the intuition that you should have, that log grows very slowly, polynomials kind of grow a little bit faster than that, and exponential functions grow really, really fast. The last thing that I want to say is this type of statement is true. Let's say comparing x squared to x cubed. This type of statement is true even if I put some very, very large constant. You know, this number is more than the number of particles in the universe. So even if I put this very large constant as a coefficient in front of x squared, still x cubed grows much faster than it as x goes to infinity. So maybe in the beginning, like I plug in x equals 1, this one will be much bigger. But as x gets very large, this is going to dominate. The way you can think about that is I'm taking this number times x times x times x times x, right? So it's this number, which you should think of as small because it's finite, times a large number times a large number. Whereas this one is a large number times a large number times a large number. So really the only comparison is this finite number, which you should think of as small, compared to x, which is going to infinity. And so again, this will be much bigger. So all of this is sort of just intuition. We're going to make this precise when we talk about limits in the next week or two.